Getting from point A to point B. For thousands of years, this was one of humanity's greatest struggles.
Journeys on horseback that lasted months were simply a fact of daily life.
Then came the 20th century, and with a spark, everything changed. Trains, cars, and then airplanes launched the era of globalization. The world became a global village.
Today, there are people who work in one country and live in another, commuting across borders on a daily basis. An incredible ability, getting from point A to point B faster than ever before.
But humanity is never quite satisfied. We keep pushing point B further and further away, always asking, how fast can we get there? We stretch the goal, making it harder with every step.
And now, we've set our sights on Mars. We're going there. There's no turning back. Once humanity decides something, it happens. Whether it takes 5 years, 10, or 50, we're going.
But when you zoom out to the cosmic scale, Mars is basically our next door neighbor. So what if we pushed point B just a little further?
What if we aimed for an exoplanet outside our solar system? Take Alpha Centauri BB, for example, the second closest exoplanet to Earth, only 4.37 light years away. On the cosmic scale, it's right there.
At the speed of light, it would take just over 4 years to get there. Let's just go and settle in, right?
But there's a problem. To make it in 4 years, we'd need to hit the speed of light. Can we do that? Unfortunately, no. So how fast can we actually go? About 32,000 kilometers per hour on average. That's just 0.003% of the speed of light. And at that speed, how long would it take to reach Alpha Centauri BB? Roughly 142,000 years. Visiting our neighbor takes a 142,000 years. So what do we say? Out of sight, out of mind.
Well, here's one idea. We could build spacecraft designed to travel for that entire duration. Ships where humanity could live, reproduce, and survive for a period nearly as long as all of recorded human history.
142,000 years. Generations upon generations. What kind of ship could we design? Where would we get enough materials, food, water, and fuel for hundreds of thousands of years? Let's skip those impossible questions and assume we figured it all out. If they can survive without destroying themselves or each other inside that ship, then thousands of generations later, our descendants might finally arrive. But what if they arrive to find a landscape nothing like what they expected? Imagine that. 150,000 years of disappointment. I don't think they'd have very kind words for us. Would you?
So maybe point B was a bit too far after all, wasn't it? A pointless journey and a pointless expense, perhaps.
But what if I told you we could skip all of that with a single step? What if you could walk to Alpha Centauri B and say, nothing to see here, turn back. In an instant, a shortcut, a portal, a hole.
A wormhole.
Yes, wormholes. Doorways from point A to point B. Bridges across the cosmos.
Whether it's 4 light years or 100,000, take the fabric of spacetime, fold it, and punch a hole through the middle. Journeys that would normally take hundreds of thousands of years could be shortened beyond imagination.
In fact, it could shorten them so dramatically that in some cases, the moment you enter the wormhole, you arrive at your destination.
And the origin of this idea isn't some far-out science fiction. It first appeared in the theory of general relativity, thanks to our man Albert Einstein. Working on the field equations of general relativity, Albert Einstein and Nathan Rosen discovered that the bending of spacetime could theoretically produce these holes. They were even given a name: the Einstein-Rosen Bridge. You might remember, we talked about this before. According to general relativity, what we call gravity is nothing more than the bending of spacetime itself.
So if spacetime can be bent by mass, then logically it should be possible to bend and manipulate it in other ways too. And the math backs this up. Wormholes don't actually violate the laws of physics.
But those same laws don't forget to mention something else. Wormholes are possible, they could exist, but they're pretty much useless.
Think of it like a tunnel drilled straight through a mountain to get to the other side.
But in a wormhole, the walls of this tunnel would be incredibly unstable. They'd collapse inward, crushing any traveler passing through in an instant.
And it gets worse. The instability in a wormhole could eventually escalate into a supernova, capable of obliterating an entire solar system.
So, unless you find a way to stabilize these tunnels, things will go very, very wrong. Your quick shortcut could end in a supernova.
To prevent that, you'd need to push those collapsing walls apart, and that's not easy at all.
Because what you need is matter with negative mass. Yes, you heard that right. You, skyscrapers, stars, everything has positive mass. What we need is the exact opposite, something with negative mass, something that extracts energy from the vacuum of empty space.
Sounds strange, doesn't it? But theoretically, such matter exists. We call it exotic matter. We just haven't found it yet.
If we could find it, its potential anti-gravitational properties could keep the tunnel open. But there is one candidate: dark energy.
What is dark energy, you ask? We covered that in a previous episode. You can check it out above. As we discussed, dark energy works against gravity, accelerating the expansion of the universe. But here's the problem. Let's say dark energy is the solution we need, and let's say we even manage to detect it. To keep a tunnel like this open, we'd need an absolutely staggering amount of energy. We're simply not advanced enough to harness that kind of energy. And let's be honest, we haven't even managed to detect it yet. And even if we solved all of that, there's still no guarantee you'd survive the journey through the tunnel. Because according to quantum mechanics, the tunnel would be filled with countless strange new particles. On top of that, the radiation levels would be so extreme they could incinerate anything that tried to pass through. That's assuming you could even fit inside the thing. And here's another fun detail you might not expect. This so-called shortcut could actually take longer than the original route. On the other hand, Stephen Hawking tells us something fascinating. Wormholes already exist, but they exist at such an incredibly small scale that we can't even detect them. And even if we could, fitting inside one would be out of the question. Think of it this way. Any surface that looks smooth to us, when you zoom in close enough, you'll find it's not smooth at all. It's full of gaps and rough edges. Scientific wonder at the quantum scale. Measured delivery, making the constant creation and destruction of wormholes feel magical. In the same way, at the microscopic level, quantum fluctuations cause tiny wormholes to constantly form and disappear. Perhaps we could detect wormholes that formed in the first moments of the Big Bang and find a way to enlarge them. Or maybe, as the universe expands, some wormholes expand with it, eventually growing large enough for us to use.
But no matter how you look at it, creating and stabilizing wormholes is incredibly difficult. According to scientists, what we should do is work with candidates that already exist in nature.
Black holes are, of course, the most important candidate.
Some theories suggest that white holes exist, the theoretical opposite of black holes. Everything that falls into a black hole gets ejected out the other side by a white hole, spewing matter into another location or even another universe. But white holes exist only in theory, and honestly, they feel more at home in science fiction.
What we actually need are electrically charged black holes. We've talked about how black holes form before.
Finding a charged one won't be easy, but these black holes could form a kind of bridge with an oppositely charged black hole. And that is exactly the definition of a wormhole. But there's a problem. Opposite charges attract each other, and that's a serious issue. It means collapse. So we need to place something between them. The answer to the puzzle. Cosmic strings.
Cosmic strings are essentially defects in spacetime that formed in the very first second of the Big Bang. These strings are thinner than a proton, yet a single centimeter of one could be heavier than Mount Everest. If you ever encountered one, it would slice through you like a lightsaber before you even knew what happened. We haven't detected them yet, but there's no reason they shouldn't exist. But thanks to their incredible tension, if you thread these strings through the oppositely charged black holes we talked about, you could achieve the balance needed to stabilize the system. But there's yet another problem. Cosmic strings aren't exactly stable either. The vibrations they produce can actually bend space-time itself. But here's where it gets brilliant. If we turn this problem to our advantage and position these strings precisely, we could generate the negative mass effect we need and finally create the wormhole we've been looking for.
But even if we achieve all that and manage to open a wormhole, there's still another mystery. Would it be a one-way trip, or could you go back and forth?
No matter how you look at it, we're facing a seemingly impossible task.
These are the possibilities we watch in awe in brilliant sci-fi films like Interstellar. But for now, they remain just that, possibilities.
You might have noticed that we've only focused on traveling from point A to point B in space. But there's another dimension to this, time travel, and that deserves its own dedicated video. In summary, all of this depends on a whole range of possibilities we haven't yet discovered or detected. Before we can even debate whether wormholes exist or whether they're safe to use, we need to understand the history and especially the geometry of the universe far better than we do today. But no matter what, isn't it exciting just to think about these possibilities, to even have this conversation? And that's why we'll keep exploring these possibilities together. But as always, until we meet again.
I'm glad you're here.
Sending love.